Hi, thanks for tuning in to Holloway Help. I'm Scott Holloway, a physics teacher at Westlake High School in Westlake, California. Today we're going to be looking at centripetal force versus centrifugal force. Centripetal, centrifugal. Which one is the real force in physics? Which one do we talk about? We're here to clear that up. I'll let you know right off the bat. This is the real one. This one's spoken about a lot of times, but the people who talk about it generally don't know what they're talking about and use it incorrectly. So we're going to clarify that this does not exist today. Thanks. I hope you enjoy it. Okay, our device we're going to be using today is a waiter's tray. We don't see a lot of them in the US, they're more common in Europe, and where they're found is waitresses and waiters will use them to carry drinks on to keep the drinks from spilling. So it works great to show centripetal acceleration. This is from the science source, and what I've done is they had a handle coming down and I cut off the handle to make it a little bit easier to do a full demonstration, a little more wow factor, so I've altered the device slightly. Alright, to begin I start with an ordinary empty plastic cup. It's helpful if you use a cup with a wider base. The wider the base, the more surface area you have for friction on the platform, the easier it is. It also helps keep your center of gravity low, the wider the base is, which is a lecture for another time. I take a bit of water and pour it in. This has just got some color so it shows up, so the kids don't think I'm trying to pull a fast one on them. I actually fill the cup in front of them, and then you can place it on the tray with the handle facing towards you, especially if you cut the handle like myself, and then you can rock the tray back and forth and get the cup at 90 degrees to the surface pretty easily. And it's hard to see on camera, but the water in the cup stays relatively level as it swings back and forth, and that's really what we want to focus on for the discussion. And so if we get good at this, and you practice a little bit, you can really impress the kids with a couple of loop-de-loops, and the water stays in the cup. The one thing you definitely want to do afterwards is pick the cup up, show that there's no tape on it, and then just dump the water out. Let the kids know that the water is, actually not a gelatin or something that's tricky. It's not a trick, it's you're demonstrating science. Okay, so we're talking about forces, and centripetal force is a real force, so, I should say that differently. Centripetal force is made up of real forces. It itself is a summation of forces. We generally write centripetal force is equal to the sum of forces along the radius, and that's given by the equation ma sub c, or mass times centripetal acceleration. So it's a sum of forces along the radius that create what we call the centripetal force. It itself is not an individual force, so you won't see centripetal force on a free body diagram, but there are forces that make up the centripetal force that will show up on free body diagrams. For instance, let's take for example our platter, our tray, when it is at 90 degrees. So at 90 degrees, the cup is sitting on it, and we'll use the cup as the object that force is reacting on, because the cup is being made to go in a circle, and so we talk about centripetal force for things that go in circles. So it's the cup sitting on here that's being pushed by something, and let's identify what that force is. Here's the tray. Here's our cup with our water. Now, of course, on the cup we have gravity acting down at all times, but the cup itself is moving in a circular pattern. And what could cause it to move in? Well, the only thing touching the cup other than gravity is the tray. And the tray is going to provide a normal force perpendicular to the surface of the tray. We're going to have normal force that way, and we're going to have some friction that's going to oppose motion. Now you got to think about which way did the friction go here. Friction, the cup, if you just held the tray there, the cup would slide off. So friction must be acting this direction. The friction is relatively minimal. In fact, the tray I use is relatively slippery, and if the cup doesn't have enough water in it, it can slide off because this frictional force is so weak. What's important though is the normal force, the force directed towards the center, is what's pushing the cup around in the circle. Let me demonstrate. When the cup's in this position, it's currently moving up as it goes in a circle. So its direction of motion is straight up. Newton's first law says an object in motion will continue going straight up as long as no other forces are acting on it. Now gravity, of course, is acting down, mg, and we said friction was acting up. This was our original velocity here. Friction's acting up, so there's nothing to take it off this linear path except for the normal force. So if it moves up, and then the normal force pushes in towards the center. So up and in, the cup is going to curve slightly towards the center. And then when it gets to this position, it's going to be going that way, but it's going to go that way and down. So it's going to get to this position, and it'll be going that way. When it gets over here, it's going to be moving this way. And from here, the tray is down the other side, so it's pushing in. The tray always pushes towards the center of the circle. And that makes the cup hit different points on a circle. So we get a circular path of the cup as it moves around. And the reason it moves in a circle is by the push from the normal force. And that normal force, F sub n, which I'm going to draw right there, is what's creating our centripetal force. It's the only force acting along the radius. So this push is in towards the center, centripetal force towards the center. Normal force pushes towards the center, and that's what we call centripetal force. But what about that centrifugal force we hear about all the time? Does it exist? Is it real? Let's take a look at what happens to the cup and see if we can figure it out. All right, I've taken our water glass and I've emptied it, and I'm going to replace it with some lumps of clay because I'm going to purposely make the cup fly off the tray, so I don't want to make too big a mess. So this will work as to add some weight to the cup and simulate the water that was in there. The kids will get the idea. I'm going to put the cup on the tray again, and what I'm going to do differently this time is I'm going to stop it when it gets to the top. And we'll see which way it goes when you stop the motion. Now, of course, centrifugal force points out away from the circle. So if I stop at the top, it should be pushing up against the tray. When it can't go up, it may fall straight down. Let's see what happens. So the slow motion replay of that. As the tray goes upside down, and when it gets to this point, the cup moves sideways still. It continues to move sideways and it follows a parabolic path down. The only two things acting on it when it moves sideways now is gravity. Well, the only one thing. It has gravity and it still has momentum moving sideways. So it wants to go in a straight line and gravity's pulling it down. There's no force shooting it upward. We don't see it shoot up in space or into the air as a lot of kids think it will. When you twirl something over your head and let go, it doesn't go straight out away from you. It keeps going in the last straight line that it was going in, and then any other outside forces like gravity begin to act on it and cause it to curve down. So there is no centrifugal force. Centrifugal force is not real. It's just one of those things that gets propagated. So to summarize what we've learned today, we've learned that since an object doesn't shoot out away from the center when it's being twirled, there is no such thing as centrifugal force. Although useful for explaining advanced physics concepts while things are spinning, it's not a real force. On the other hand, F sub c, centripetal force, is made up of real forces. This does exist, and it always causes an object to move in a circular path. The force, F sub c, is directed towards the center of the circle, not out away. Towards the center, not away. I hope that cleared things up and you learned something new.